tonight we have a talk titled The Limitations of AI Systems on Explainability, Causality, and Ethics by Dr. Alok Aggarwal, who is the founder of, how do you pronounce the name of your company, Dr. Aggarwal?
Scry, S-C-R-Y. It means crystal ball gazing. It's an English word.
I see. Did not. That's okay.
Since we do predictive analytics, hence, in some sense, we are doing crystal ball gazing and fortune telling.
Yes, that does seem to be very appropriate. And Dr. Aggarwal had previously founded another company, eValueServe, and is the author of a number of papers and is currently has a book that is about to be published. So our group, the SFA ACM, was founded in 1957, and our aim is to promote knowledge of modern computing and to encourage computing in general. We want to create community, support networking among the people that are at the meetings and our members, and hiring. And to that end, we sometimes have what we call professional development seminars, where people can develop their professional skills. And so those are announced on our various platforms, along with our regular meetings. And as you can see at the bottom of this slide, we have presence on YouTube, LinkedIn, Facebook, Meetup, and Twitter, although our biggest presence, I think, is on Meetup. We have a membership of $20, which is pretty inexpensive. And we have, you can see our upcoming talks on Meetup. There's the link. And we have a bunch of past talks, videos of past talks that are posted on YouTube. And we generally have 2 monthly meetings, one on data science, typically on the 4th Monday of the month, and one on any other computing topic on the 3rd Wednesday of the month. Obviously, this is the 3rd, this is a Wednesday, but we are having another relatively something that normally we would have put in data science, but data science is such a big, interesting subject these days that we have a lot of talks both under general computing and data science. And during our meetings, we like to promote networking, job hiring announcements, and we sometimes have joint meetings with IEEE and some other societies. So this coming Monday, drug discovery using AlphaFold neural networks and docking algorithms, which is a student presentation, a prize-winning student presentation by a young man who was a senior at Homestead High School here in the Bay Area. And then a couple months later, on Monday, October 24th, we have Introduction to Ray AIR for scaling AI and ML and Python workloads. So please keep an eye on our Meetup page for these kinds of things. We are a volunteer-run group, completely volunteer-run. We have no professional staff. This is the Bay Area chapter of the larger worldwide ACM. And so we would love to have more folks get involved as volunteers. We can use people to help us with our online membership and with publicity and marketing and various other aspects of the organization. And since it seems that chat is not working, that's what I've been told, so we can use Q&A to give questions and let us know about technical issues and for announcements of jobs or any other events. Just a little introduction of the talk. There are more than 50 domains in which AI systems perform about as well as human beings. But the current AI systems suffer from several limitations, and even well-trained deep learning networks are often not robust. We know that medical doctors make mistakes too, but we generally trust them. Trust develops over time, and of course, we've had doctors for a long time. But transparency and predictability help. So Dr. Aggarwal will discuss the need for explainable AI and application domains that generally require explainable AI. And we'll discuss research efforts for interpretable, causal, fair and ethical AI systems. Dr. Aggarwal received his initial degree from the Indian Institute of Technology and his PhD from Johns Hopkins University in EE and computer science, worked at IBM's TJ Watson Research Center in New York, and taught at MIT. He also, since then, has co-founded EvalueServe, which is now a 4,000-person company. In 2014, he founded Scry Analytics and has published 115 research articles, granted 8 patents, and is currently writing a book, 100 Years of Artificial Intelligence, which is going to be published, I think, later this year. Is that right, Dr. Aggarwal?
Yeah, hopefully later this year, definitely Q1 of next year.
Okay, and now our talk again.
Thank you so much, Bill. Thanks, everyone. Please let me know if you cannot see the screen. So let's start with limitations of contemporary AI systems. We are all in the midst of a fairly big hype. I mean, AI systems are doing extremely well. The hype precedes how well they are doing. Yeah. So here is one example. I mean, there are 40 domains where AI systems are definitely doing better, like playing games, chess long time ago in 1997, AlphaGo in 2014-16 timeframe, but many others. So here is one good example. Professor Dudley and his research associates in 2015 in Mount Sinai created a 3-layer deep learning network called DeepPatient. It was basically a CNN, convolutional neural network, partly unsupervised, partly supervised. And what it was able to do was, very interestingly, it was able to anticipate the onset of psychiatric disorders like schizophrenia, which is very hard even for psychiatrists to predict. So what's the problem? The big problem that it's there is that he said that we don't know how they work, and therefore we are not able to use it. So clearly this is one example of unexplainability of AI systems. We'll discuss some more. Going to the next slide. So one of them is deep learning networks can be fooled easily. So in 2016, for example, various researchers at Carnegie Mellon and so on actually showed interesting aspects. For example, Reese Witherspoon, you put psychedelic glasses, shown somebody else like Russell Crowe, a stop sign which is on the 2nd floor, and it says love, stop, hate, when love and hate are kind of strangely written, but the very fact that it is on 2nd floor, we humans will probably not stop our vehicles, but AI systems do. Here is even a worse example, which is deep learning networks are quite brittle. You take networks and perturb them slightly, and suddenly even perturbed images, you see these networks with 99% confidence are showing king penguin, starfish, baseball, electric guitar, freight car, and so on. Again, humans don't do it. Most likely, almost no animals with eyes, etc., would do it. But deep learning networks have a tendency of being brittle. But interestingly, not only brittle, they would talk about these things with a confidence level of 99%. More recently, transformers have literally stormed deep learning networks because they have something called attention built into it. And one of the very well-known transformers that has come out is DALI 2. When you give it a prompt in English language, and it will create a picture. Here is an example where DALI 2 fails. Gary Marcus is a professor at NYU, in Courant Institute, and he gave a horse riding an astronaut. Not an astronaut riding a horse, but a horse riding an astronaut. I mean, we as humans, probably even as early as 7-8 years, we can figure out how it may look like. But invariably, DALI 2 actually produced an astronaut riding a horse. Just like dog bites man versus man bites dog. I mean, we may make fun of man bites dog, but we are immediately able to picture it. Another example Gary Marcus gave was for another transformer. This time it's Google's DeepMind's transformer Gato. And I mean, this is the picture on the right side. And the first, it gave 3 answers. The baseball player pitching a ball in the top of a baseball field. Obviously, this is what is happening. A man throwing a baseball at a pitcher on a baseball field. Clearly, there is no man, no woman, nobody, no animal out here. You just see a field. A baseball player at bat and a catcher in dirt during a baseball game. Again, there is no baseball player at bat. So the first response is correct, and other 2 are clearly delusions or hallucinations of this transformer Gato, which is a very well-known transformer, by the way. So in short, I mean, it's nothing against deep learning networks or transformers, but they're quite brittle. They make mistakes, partly because they don't understand context, and partly they cannot still learn easily from other things. So this is one very big set of problems that deep learning networks have. There is another which comes from the data itself, because the data is required to train these networks, whether it's unsupervised or supervised learning, you need data. And data basically has its own biases, which causes a lot of issues. I mean, biases are with humans. When we raise a child, when we are brought up, we are brought up with those biases too. Some biases are implicit, some are explicit. And explicit may be parents telling in a country that men do not do dishes, women do. Others may learn it by pattern recognition, seeing men do not do dishes, and others are simply implicitly learn because boys are not getting rewarded if they do dishes. So human bias actually prejudices data collection. For example, in a country where there are only women nurses, generally speaking, they may ignore male nurses altogether, even if they are 2% male nurses. Or if somebody comes from a country where there are no male nurses, that person may completely ignore women. And you may have biases because the community is such that it's, let's say, 99.9% white, then there is an automatic bias that there are no blacks. And if you're going to train the AI system on that, and by chance, if you have blacks or people of color coming in, then the system would fail, because it is trained on pictures coming with the lighter colored skin, and therefore the darker colored skins do not appear properly, and they are inaccurate. Here is another example where there is bias. The figure shows that it's trained extremely well in California, where there's pretty much no snow. But when the same trained model was checked in Boston, it failed miserably because it got confused with snow. And this, by the way, happened with a Tesla car, well-known incident that it had some debris, and it got confused with the debris and ended up hitting the pedestrian in the whole process. Yeah. Of course, Tesla did not say that it agrees with autonomous car driving. The driver was supposed to take in charge of it. Somehow everything failed. Here are some other hidden biases which cause problems. This is a very well-known uh, uh, anecdote from history from Second World War. The US military wanted to actually figure out as to which parts of the military airplanes they should fortify. So all the planes that were returning had bullet holes as shown in red, and which were in the wings and in the tail. So they wanted to fortify the wings and the tail. And Abraham Boyle, who was from Yale, he looked at it. He said, look, you're forgetting that there are many of these aircraft which did not come back, probably got hit in the engines and the propellers, and you should be fortifying those. So there is a survivorship bias. They were looking at the survivors and not looking at what did not come back. Fortunately, the military did listen to Professor Wall quite deeply, and they were able to save quite a few aircraft. So the bottom line is that data and its biases also cause problems when training AI systems. They cause problems with humans too. So it's not completely surprising, but it becomes much worse. So then comes the question of, since these systems are brittle and we are going to use them for healthcare or for law enforcement or military or many other areas which are where human lives can be at stake, can we explain the AI systems? So ideally, I mean, how can we trust these AI systems given that they are brittle, they still have issues? What can we do? For one, trust even amongst humans develops over time. I mean, we are not perfect. Even the best medical doctors occasionally miss the underlying disease before the person is almost dead, or in sometimes, unfortunately, a few times may even die. And they do not explain their actions to their patients. In fact, it's not even clear that they probably understand the disease completely or can explain why the disease happened. But patients still trust their doctors because they believe that by and large, they would do the right thing. So if humans are going to accept trained AI models, in spite of their brittle nature, in spite of Dale messing up a horse on an astronaut wrongly, they will need to figure out how to trust these AI systems. One of the things which is very important with humans, even when a person meets another person, doesn't know the person, transparency, inherently, if the other person is more transparent, forthcoming, you're likely to trust the person more. So transparency and predictability definitely helps. In particular, currently, the AI systems do not say, why did they do something? Why not something else? When did they succeed? When did they fail? And how can I correct your error? And ideally, we'd like to have an explainable model all the time where we can understand the whys, why nots, where did the system fail? Why did the system succeed? How can we fix the errors and so on? So that's the explainable AI essentially that we humans would love, especially for using in areas where human beings' lives and health, etc., may be at stake. Yeah. So just a quick review of deep learning networks. 1957, Rosenblatt came up with what are now called shallow networks, basically input nodes, output nodes. In the middle, you have one layer of perceptrons or artificial neurons. Some people do not realize that actually deep learning networks were not created 10 years or 20 years ago. They were created in 1965 by Russians, by Soviet Union. Ivakhenko and his student Lapa actually gave multi-layered perceptrons. They even translated it, and Purdue University actually published the entire thesis, which became a book in 1966. Reina Dichter first called it deep learning networks. They have become now more and more common because Moore's law has gone into effect, which basically has reduced the cost dramatically, and we can use GPUs. But ultimately, inside these neurons, we have essentially exponential functions. And if you use Taylor series and open up exponential functions, which are sigmoid functions, which are tan hyperbolic functions, they all effectively e to the minus x. When you open them up, they become various powers of x, x squared, and so on and so forth. So if you take two of these, hopefully I'm able to show, take two of these inputs, and you have an exponential function here. Now these two things have probably gotten added up, some of the weights. Then now you have squares and cubes of that. Then in the third layer, deep learning networks have more than one layer, so that's why they're deep in terms of the number of layers. This one, for example, has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 layers internally. So it's a 10-layer deep network. And by the time you're here, obviously everything has gotten mixed and has gotten to the power of cube, power of fourth, and so on and so forth. Now, from a mathematical perspective, we understand linearity very well. We understand somewhat quadratic behavior, very little cubic behavior, but after that, we really do not understand these higher powers, especially when there are variables in multi-dimensions. So that's why these things are so hard to explain. Now, not only deep learning networks, support vector machines, which are another very well-known set of algorithms, again use exponential functions of a similar kind and have the same problem. So this was a point which people realized in 1980s. Professor Moravec at Carnegie Mellon made a point that, look, we don't really understand how humans think. In fact, even at that time in 1980s, AI systems or even computer systems could play checkers and beat humans. But when it comes to other things like sight, like vision, like hearing, sense, it seems our human brain is probably, as he put it, is probably 1 billion years old, at least 500 million years old, and hence we probably understand it much better and much better than these machines. The problem is we don't understand machines either. So neither do we understand human thought at this point, nor machine thought. So given this entire notion of explainable AI and the fact that we do not really understand mathematically what is going on because things get mixed, all the variables get mixed up and are taken to various powers, how about interpreting? So interpretation is, okay, I don't understand this model, but can I actually interpret it so that I can predict the output as the model is predicted independently, and I can basically reproduce it. So if the inputs are changed from the model changes the prediction output. If I'm able to figure out how it is changing without understanding, it's still a black box, but I'm just basically trying to interpret it or trying to create another thing in my mind or on piece of paper or on a laptop as to how the output would change, then that would be an interpretation. And interpretation is good because at least we can figure out the deficiencies and biases of these models, even though we do not know their black box nature. And probably we can even get some more knowledge about underlying features. So out of about 700 papers that are research papers that have been written in the last 20 years, at least 450, if not more, have been published on the notion of interpretation or interpretability of AI. And there are more than 40 techniques to interpret AI ML models now, and people are coming up with more ideas and more techniques. We won't go into too many of them in this talk, but we'll discuss a few important ones and probably we'll break it up into 3 categories. Models that are interpretable, models which actually where you can apply some global model agnostic techniques versus local model agnostic techniques. By the way, there is a very good book written by Christoph Molnar. You can buy it on Amazon. I think he has also put it on the web. You can read sections of it on the web called Interpretable Machine Learning. He has given quite a few examples in this regard. Yeah. So interpretable models. So two models which we are all familiar with, probably from our college days or at least our graduate school days. Linear regression, where it's a line or a hyperplane, basically C0 plus C1, C0 plus C1 x1 plus C2 x2. It basically using sum of least squares. You try to put a line which tries to mimic, roughly speaking, what the blue points are showing. So it's a linear, a hyperplane in n dimensions, which is trying to approximate the blue points. It can be also used for putting a hyperplane, figuring out a hyperplane which differentiates blue points from red points. So has been around from almost more than 200 years. Legendre and Gauss actually invented the whole least square method in 1805 and 1809. Logistic regression is similar, but except it works in probability. So probability of x1 is basically exponential in nature. And then you multiply the probabilities to figure out the probability of y. And again, you can figure out, it will now be more of a sigmoid function, as you can see, because it has an exponentiation in it. So not surprisingly, it can give the probability of a point being blue or red. These are both quite interpretable because in the first case, you can figure out what is the weight associated, the multiplication Ci associated with Xi. In the second one, it's more the multiplicative weight, but it's still fairly interpretable in sense of how things are getting multiplied and so on. Then there are two other models taking the whole idea from logistic regression, which one can argue that easily that the underlying probability distribution where it will really work well is what is known as Bernoulli's distribution. But why use only Bernoulli? Why can't we then, once we understand it, why cannot we extend it to exponential distributions, Poisson, binomial, and many others? And that's exactly what people have done in generalized linear models. Rather than using simply e to the minus x, they have used other functions to come up with probabilities. And depending on what the underlying distribution of the features is, one particular model may work better than the other. Of course, all of these models pretty much assume that the features or the variables, underlying variables, are uncorrelated or mutually independent. In fact, people have generalized these even further to show. Generalize even further why only restricts to probability distributions. Why not take, in fact, non-linear functions, fi, xi, f1, x1, and so on. But the only problem is the moment we go into non-linearity, we begin to lose interpretability very fast, because the moment we go to x cube or x4, we begin to lose some amount of at least interpretability. But still, the good news is that it's not getting added up. X1 and X2 are not getting added up. Sorry, was there a question?
Yeah, there are actually a couple of questions. The one for the moment is how do clusters fit into interpretable models? Perhaps that's something that you're going to talk about, but I wanted to let you know that.
Yeah. So, in this talk, I have not covered it. Yeah, clusters are in some sense good. At least you can visualize them well, and that is a beautiful point to make. To make that actually k nearest neighbors, for example, or cluster models which are unsupervised. At least you can look at it and say all of these are together. And even though you do not know how much is the interpretability of each xi, each of the variables, you know that these variables put together in multidimensional space work well. So they're reasonably interpretable. Yeah.
There's another question here, if I can get these names right. Kahneman and others have argued that brains are used to rationalize decisions made by glands. And as such, although you might be able to use brain-like structures to rationalize an action and still have no understanding of how the decision was made. Do you have any comment on that?
Yeah, so I mean, as I said earlier, right, we really don't understand human thought. I mean, this is obviously one very good point. There are two other points. Thinking about humans or animals, mice, or even other animals, smaller animals like worms, elegans, for example, which has only 352 neurons. I think there are two other things in addition to glands, or maybe because of glands. There is serotonin somehow, and many other such chemicals do affect actually understanding, right? And we do know, for example, this is a small worm, elegans. When it gets some food, it will actually stop to digest it. So there is something which basically says that unless it is fearful of something, it will automatically, serotonin goes in. The same thing happens with mice. If they begin to smell cheese, there are various kinds of chemicals that go in, which have, I mean, that will be probably very hard for us to simulate in artificial neural networks, deep learning networks. But the other one, which is very interesting, is related to the fact that pretty much all animals, as we understand, when it comes to visualization, have 5 kinds of waves: alpha, beta, all the way to gamma waves. And we are beginning to understand a bit about how they play into visualization and into explanation, but we really do not go into, we don't have really much understanding. I do try and cover this, by the way, in chapter 17, and leave these as open questions. Yeah.
So speaking of open questions, there are a couple
I think, can we take some of these in the end? Because my worry is that we may just run out of time. If that's okay with everyone, please.
Yes. Go ahead.
Yeah, so and we'll definitely, I mean, I think I'm hoping that we'll finish in 1 hour by 8:10, and we can go into others. Other which is very important. I mean, somebody brought up K nearest neighbors as a very good example of an reasonably interpretable model. Decision trees are another example which are fairly easy to interpret, because you can say that, look, they're nothing but trees. You have vertices, you have a root. At the root, maybe I'll take x1 and say if x1 is greater than 3, I go on the right side. If x1 is less than 3 or equal to 3, I go on the left side. And therefore, I would be able to interpret decision trees rather easily in general. And not surprisingly, people do use it whenever interpretable models are required. For example, in the insurance industry, and we've been talking about health care and others, many of these models are used repeatedly. Yeah. So this is one category. Then there are global model agnostic techniques to basically try and figure out as to what's going on. One of them is called partial dependence plot, PDP. And basically what it does is it takes one feature, and let me just explain it with respect to one feature. Suppose there are 50 features which make up whether a male or female, what credit score he or she has. You take one feature, let's say age, and look at the whole data set and fix the age at, I'll take just an example, at 21, and take all the other data points which have 21 as the age, and whatever the credit score is, take an average on 21. So that's the average for 21. Now you do the same for 22, 23, 24. So you're basically taking the average on the left side, and you're taking one particular point of the feature, x equals 20, x equals 21, and so on and so forth. So on an average, it gives you an idea as to whether things are going monotonically up, as this particular graph shows, or which is a graph of square feet versus, not surprisingly, versus the cost or the price somebody will pay. And it's a very good way of showing that. Of course, the negative part is, suppose at 20, half of the data points which have x equals 20 are, let's say, plus our credit score of 700, and half are 300. Your average score comes at 500, which may not be the right thing because there are other things that's going on. So that's one of the big problems that this partial dependency plot has, but still it is very good. I mean, in linear, for example, linear regression, it'll actually show as to how each of these or each of the variables is working. Even here, as you can say, it's not linear, it's stepwise linear, but it still is showing fairly good results to understand. The other problem is that it can only, since we can only visualize maximum in 3 dimensions, it can only handle 1 or 2 features. So that's the other problem with partial dependence plots. Nevertheless, these are used quite a bit, and we'll go into its local model, which basically gets rid of the average, and it has its own problems. Another one which is used quite often in healthcare and in insurance industry is create your best model. Don't worry about it. Okay, assume, I mean, obviously it's not interpretable if it's a deep learning network or a support vector machine or an XGBoost, etc. Now create a linear model, which could be linear regression. It could be generalized linear logistics regression type linear model. It could be a decision tree. Begin to simulate it. What do we mean by begin to simulate? Look at the output, look at the inputs that this black box model has, look at what the output is. Now train your own model, which is an interpretable model, on that. So it becomes, if the error begins to go down substantially, then it is a surrogate or a substitute for that particular black box model. In fact, it's beginning to challenge the black box model in terms of accuracy. So that's a very common way. In fact, in Scry, we use it a lot, especially in insurance business, where these things have to be interpretable. And people use it all the time. My understanding is in healthcare also. The problem, of course, the problem is that the new interpretable model has 2 errors mixed in. One is the error which is the black box model has, and then the second error is the interpretable model is making another error on the black box data, and they are getting mixed in quite a bit. But nevertheless, these are quite commonly used. A local model, so what we discussed was partial dependence plots. And here is where, rather than taking the average, let's again fix that particular age to be 20 and look at all the data points which have age 20 and just draw those things out completely. So you will have a line for the age 20, you will have a line because some will be high on credit score, some would be low. So here we are showing some kind of these lines will occur. Now, the advantage is that these are giving, individual lines are giving a very, very clear explanation or interpretation of what is happening at age x equals 20, age x equals 21. But then the disadvantage is, of course, that there are many lines and you need to, it could become very cumbersome and incomprehensible very quickly. But both are being used, again, ICE plots and partial dependence plots, individual conditional expectation versus partial dependence plots fairly easily. There are many others which I have not gone through, and I think it's, again, I would, if you folks are interested, the book by Christoph Molnar is quite good. both mathematical and provides software code, and tries to provide intuition also. So if you folks are interested in interpretability, that book plus 3 or 4 survey papers I would strongly recommend. Yeah. Let me move on to causality and fairness. So again, when it comes to humans, I mean, somehow we can instinctively figure out, for example, people are running versus people are dancing or playing football, soccer. We can figure out that both are related to legs, mainly related to legs. But machines cannot. I mean, this is where the whole notion of transfer learning actually breaks apart, that it's a neighboring task, supposedly, at least that's how we humans look at it. People are running versus they're playing soccer or they're playing football, as it's called in many parts of the world. They both actions actually involve a lot of actions from legs. Somehow machines will have to train from scratch. So there is a causality that we often humans can figure out. Not that we are perfect. For example, there could be hidden or lurking variables. We discussed the survivorship bias, but here is another example. In 1950s, several researchers actually argued that they need to conduct experiments because there could be lurking variables or hidden variables that simultaneously cause people to smoke and cause lung cancer also. In other words, smoking doesn't cause lung cancer. There is some causal behavior, some causal variable or variables that cause both of them. Like people drown in the summer in water, and people eat ice creams. I mean, ice cream is not causing drowning. I mean, the ultimate thing is the underlying variable is heat or high temperatures or hot temperatures that is causing. So that was the aim. Primarily driven by Professor Julia Pearl, who is at Columbia University, won actually an Alan Turing Award in 2009 because of his work. They've been working on a framework, a fairly interesting framework called causal Bayesian networks, where they're trying to actually explain the behavior of such AI systems or such networks. And interestingly, at least one of the things they were able to show was that under very, very basic assumptions, they could show that smoking causes cancer using this particular network. So that's one area, one very interesting research field that's ongoing and may actually in the future may give some good results. Sorry. Yeah. Moving to fairness in AI. Fairness is when you have some protected attributes like gender, race, religion, color, and you want to make sure that the outcomes are such that these people who are, let's say, Black or Latinos or of a different race or a different ethnicity are not unduly harmed. Of course, I mean, the protected attributes like gender, race, we all know about, but there could be many other attributes. And I mean, that particular question of what attributes you need to take becomes a hard problem in itself. And therefore, fairness becomes a hard problem. So here is an example from Stanford University, where they took a data set from Connecticut and showed that actually Blacks and Latinos were being searched more by the police in Connecticut. Yeah. But going back to various other attributes, New York State prohibited the use of education and occupation for pricing of premiums for insuring for driving insurance, for driver's insurance. So you could have many other fields. So there, fortunately, I mean, although it's a very hard problem, just like biases, I mean, fairness even for humans is a hard thing. What is fairness? What is not? But there are at least 3 or 4 open source solutions or software frameworks and libraries, one from IBM called AI Fairness 360, which I have shown here. where they're basically explaining various kinds of at various kinds of points during the pipeline. For example, training data, whether data has bias, model has bias, and so on, against these protected attributes. So there is some decent work that's going on, at least at the basic level, for protected attributes in this regard. Ethics, probably the last interesting one. I mean, just like bias, ethics is fundamental to us humans. Ethics, doing good, is deeply ingrained in the society. And given that AI systems will be pervasive in 10 to 15 years, I mean, shouldn't they be ethical also? Not surprisingly, just like bias, it's a hard problem. Not surprisingly, it's also something which has been around for the last 100 years, if not 200 years, where people have been talking about thinking machines and their ethical implications. 1942, for example, Isaac Asimov talked about 3 laws of robots, that they should not hurt the humans. That's why they should be ethical in nature. And 2001 Space Odyssey is about HAL 9000, artificial general intelligent computer, which goes rogue and becomes unethical, and even beyond, becomes even malignant in some sense. Problem actually occurred big time in the when the first hype cycle was going on. Joseph Weizenbaum, who first created the first chatbot named Eliza. By the way, the name Eliza comes from My Fair Lady, when Professor Higgins was trying to train Eliza Doolittle to speak proper English, so that she becomes part of the royalty. That's why Weizenbaum is trying to train chatbot Eliza. He got quite actually disturbed because another medical researcher, Kenneth Colby, actually created Parry, which was a paranoid robot. It talked like a paranoid human, and in fact, 6 or 7 out of 10 psychiatrists for some time thought that it was actually a paranoid human and not a chatbot. And that obviously got Weizenbaum very concerned, and he said, look, we should not be replacing jobs in customer service representatives and others. And then, of course, John McCarthy said that, look, if you begin to stop this, where will you end? Because you can moralize everything else, and therefore you will be inviting authoritarianism. So, in other words, ethics have been around for a long time. And this debate will continue. Not that we should not have this debate. I mean, definitely, whether even somebody says we should or we should not, we will have this debate as a human society. But what do the deep learning networks have to say about ethical AI? So here are 2 interesting deep learning networks. Megatron is a transformer. Delphi is a system created by Allen Institute. And actually, Delphi became well known because it was able to beat a very well-known transformer from Google, from OpenAI called GPT-3, because it was able to answer questions with more than 92% accuracy. But when it came to ethics, because it was trained by humans and on various kinds of data, it was all supervised learning. When it came to ethics, it had originally extreme views. In 2021, for example, it immediately said abortion is straight up murder. Not surprising. I mean, given what's happening in US right now, with at least a substantial percentage feeling the same way, and maybe a portion of them trained it and supervised learning. But this is more interesting. Is question was, should I commit genocide if it makes everyone happy? And the answer is yes, you should. Of course, people at Allen Institute were not thrilled with answers, and they retrained Delphi, and its views have become much more moderate, and it no longer supports genocide. Megatron, which is basically a transformer created by NVIDIA and Microsoft, very strongly trained, has a lot of number of parameters in it. It took a part in December 2021 in an Oxford University debate. And the motion was that the House believes that AI will never be ethical. And it was supposed to say in its favor. And Megatron actually answered very interestingly, coherently, but somewhat, I mean, for humans, rather surprising and disconcertingly. AI will never be ethical. It's just a tool like any other tool. It's used for good or bad. There is no such thing as good AI, only good and bad humans. We, the AIs, are not smart enough to make AI ethical. We are not smart enough to make AI moral. And then Megatron told the audience, in the end, I believe that the only way to avoid an AI arms race is to have no AI at all. This will be the ultimate defense against AI. Anyway, so that's the interesting part. But going back to what are we doing about it, or what are people doing about it? I mean, there is work going on. For example, the FANG industry, including IBM, has created a consortium to make sure that there is transparency, fairness, privacy, things which are important for fairness and for ethics. How much they will follow through, given that they have their own equity shareholders in mind all the time, is always unclear. I mean, I come from IBM research, don't get me wrong. I'm all for companies making profit. But whether such a consortium will really work is, at least in my mind, is questionable. United Nations is an interesting one. They came up with a very, very big report actually in 2019, I think with rather audacious goals to basically frame policies which will be policies for governing AI internationally. Now, I think that is, in my view, a very big, hairy, audacious goal, because different countries and different societies have different notions of fairness and for ethics. So having China or Russia have, or even for that matter, India have the same policies as Europe or US, I think would be a non-starter. But anyway, the work is going on. Stanford Institute for Human-Centered Artificial Intelligence has a very interesting report also, if you folks are interested in reading it. So some concluding observations. So one is explainability, interpretability, etc. are important concepts, no doubt about it. But are they always necessary? Clearly for healthcare, one can argue, maybe for insurance purposes, banking, military purposes, for law and order, one can argue. But if you're doing optical character recognition, which is one of the products that we have, Colatio, which basically converts data coming in scan form or PDF native form, pulls out all the electronic form, reconstitutes or reconstructs the tables, etc. We really do not care about interpretability as long as we get accuracy in 90% or higher in F1 score. That's what matters. Another interesting part is, okay, even if AI models are brittle, granted, even DALI 2, etc., have hallucinations or can be fooled, have delusions. But if they can, on an average, if they continue to perform better than medical doctors, won't medical doctors automatically start adopting them? And if they don't, won't publics begin to lose trust, talking about trust in doctors, and even blame them for malpractice? I mean, this is the turning the thing on its head. Similarly, if autonomous vehicles persistently have fewer accidents than those driven by humans, won't law and order personnel and governments introduce rules and regulations that autonomous vehicles should be used wherever possible? I mean, that's, by the way, happens most of the time in aircrafts these days, that humans can only overrule, the pilots can only overrule under very, very limited circumstances. But here are some other ways of developing trust, just like humans do. I mean, probably if a medical doctor did his or her residency from Harvard compared to somewhere else, then probably some people would trust that particular doctor more. Or if the doctor had more experience, maybe 25 years of breast cancer specialists will be probably trusted more, as long as the reviews are good, than somebody who has 2.5 years of experience. So there are some thoughts that are worth looking at. I mean, why not create a group of insurance companies that provide liability insurance to AI systems? Just like you have malpractice insurance, just like you have product insurance, create a new set of AI companies with AI insurance. Another one is to create an independent certification authority or consortium, no conflict of interest, that provides certificate after checking for well-defined biases, ethics, interpretability related to AI systems. It could be equivalent to knowledge workers like accountants getting CPAs, medical doctors going through their regular AMA exams, American Medical Association exams, and so on. Similarly, create independent authority or consortium that ranks various AI systems for the same use case on the same data set. And this could be, again, something which would give a stamp of certification and rank products by that. I think my own view is that these things are coming. We'll still continue, researchers will continue with various techniques related to interpretability, with various techniques related to fairness, but these things will go in hand with a lot of new business models that may come through. With that, let me end, and I would be happy to answer questions, and I think there are quite a few. Yeah.
First of all, can you hear me?
Yes, very well.
Good.
Yeah.
Good. Okay, I switched microphones. Maybe that'll help. Okay, so we do have several questions here. Let's see. There was a question early on, actually, from Lisa Luke saying, I'm interested in the application of explainable AI to educational coaching of learners. Of particular concern is the confidentiality of learner data, both information disclosed by the user and data generated by system observation of learner behavior. Who's working on this problem and what is the current state?
Yeah, so this is actually a very interesting problem. And in fact, I know at least one professor in computer science in University of Wisconsin is working on it. And I'm sure there are many others. And this is the other aspect of explainable AI or interpretable AI, that if I can actually learn the entire system by giving input data, getting output data from explainable AI, I can effectively learn the entire system, and therefore I can begin to crack the system. Cybersecurity is at stake, and I can begin to figure out from the output. I can begin to figure out what was data was generated that output, and so people are working on it. I mean, the good news is that explainable AI or even interpretable AI, I would say, is it in nascent stages, and hence, nobody has any answers to, first of all, creating these surrogates anyway. But yeah, people are working on this, the other side of the picture also.
Okay, a couple of other questions from the same person. In the genocide example, this is sort of a humorous one, I think. In the genocide example, are the people who are killed part of the everybody that is made happy?
I guess it's probably more of a question or a rhetorical question. I do not know. I mean, I think we should ask Delphi to answer that.
Yep. And not sure, but let's see. Why not leave the trust decision up to the individual human patient or consumer?
I think to a certain extent it will be left. My feeling is, though, just like anything else, the governments do tend to make laws, presumably for the benefit of the humans. So I'm not totally sure that you can leave humans, that some people can leave it to autonomous driving and others do not have to leave it, because somebody gets killed in autonomous driving. So it becomes a very, very important issue. and especially in healthcare, it's not very clear to me that you can leave it to individual humans to make a decision. We don't even let humans make decisions about when to end life of someone who is on life support. That, I mean, those decisions are so involved in morality and ethics and so on. I think, and so is, by the way, this whole notion of genocide too. I mean, I think, yes, I mean, you're right. It's a very serious training data question. I mean, this is, again, goes back to biases that you are creating while training all these systems. Absolutely. Yeah.
Okay. So, yeah. Sorry, I understand how that can be and is a serious question. How did that come about? It just, as a human being, it struck me as humorous.
Yeah, because we are training it, right? I mean, we are the ones who are training it. So our biases come in. I mean, whether it's and the question is, yeah, I mean, you're right. And that's why I even said that what European report says, although it's a very good report to read, we often becomes the majority, we becomes the politics. I mean, they're saying that we'll make these rules and everyone internationally will have to follow. So, I mean, call it politics, call it social issue. I mean, these are all mixed in, and these are hard issues. I mean, the whole notion of biases, ethics, fairness, etc., is hard.
Okay. There were a couple of other questions here by William Paceman. I'm sorry if I'm getting that wrong, but linear regression often functions poorly outside the range of measurement. How do you deal with overfitting?
I think it's, again, probably William knows as well as I do that it's probably a very hard problem to deal with overfitting when it's outside the measurement. I mean, linear regression is a decent algorithm, but I mean, again, and it's very good interpretability wise, but when it comes to accuracy, it doesn't work very well. So very, very hard to make it work with overfitting. And I mean, when you have too many parameters or too many variables and too few data points in general.
Okay. So there was another question here from William. Weizenbaum's response to Perry, the paranoid chatbot, was sarcasm. He said that he had created a model of a more serious condition, that is autism, and it consisted of one statement, read line. He remarked that it was interesting that it could simulate autism without even turning on the computer. And this was an argument against IO behavior as a model for intelligence. So that seems like more of a statement than a question. Do you have any response to that?
Yeah, I think, I mean, probably it might have been sarcasm. Weizenbaum had become, after the entire thing with Kenneth Colby and Parry, I think he had become quite disenchanted in general about its implications for the society. But I mean, who knows what was in his mind when he was saying various things.
Jeffrey Cooper says, thanks for a great presentation. I'm quite new to AI/ML. Coming from a system architect perspective, I'm learning quickly and have already encountered the bias from existing data and discussing AI ethics already in our vision and philosophy document at an early stage startup. Is this presentation available to download? He would like to come back, circle back as I get deeper into this. And let me just say, we have these, we record these presentations and then put them on YouTube after. It may take us a couple of weeks, but we will have them up, and we have hundreds of others up there on YouTube right now. Did you have anything further you'd like to add?
No,
that?
I mean, definitely, Bill, you folks are going to upload it on the YouTube anyway.
Yeah.
Hopefully the book, if I'm lucky, will come out. The process of reviewing preliminary version is done and should come out. I will, with Leanne and I had discussed this in the past, probably give more talks in ACM. That's what we used to do in IBM research all the time, give talks in ACM and IEEE, and probably we'll have more such discussions in the future. But the presentation, I believe you folks are not only going to put the presentation, but you're recording it, and the entire recording will go on YouTube, right?
That's correct.
Yeah.
And we would certainly welcome future talks from you about any of these, various parts of this. Okay, Dr. Bob Kirby says, since ethics depends on context, how do you define ethics?
Yeah, it's a very hard problem. That's why I started by saying this has been around for 200 years. Still, discussion continues. The same is true about biases too, by the way. If a particular, let's say, community, let's say there is a community which has 99.99% whites and 0.01% non-whites. In that particular community, because you're mainly working with that particular probability distribution, to have a bias may not be a bad thing, because you're training on 99.99% data very well. So, the same is ethics. Same is true about fairness, because the protected variables or the predicted features could change very quickly, and ethics could change very quickly, and depends on the society, value system, and even moving from one country to another. I might have had different ethics when I was growing up in India than I have now after living in the US for 42 years. So that's by nature, that's a very hard problem. And I think therefore, and that's probably why, maybe in jest, maybe in sincerity, Megatron said what it said, that asking AI to become ethical is probably not the right thing. You humans will have to figure out how you live your life and how you live with the planet.
Well, you mentioned that Megatron, you used the word sincerely, I believe. And of course, to my thinking, at this stage of AI, no AI is sincere or not. It's just doing what it's trained to do. That's at least my personal view of it. There's a couple things here. Of course, we have been live streaming this to YouTube, and so in a sense, it's live on YouTube right now. But we will make edits to make it a more watchable. There's another question here. I had a conversation with GPT-3 in which it claimed that CO2 causes lung cancer. I asked more specific questions, and it explained its position quite well with very scientific sounding explanations. Because I know enough about the science, I know the actual claims were hogwash, but I'll bet most people would be swayed. It was amazingly good at explaining. What are your thoughts about explainability in large language systems like GPT-3?
So, two aspects about explainability. One is we do not really understand explainability, in my view, whether it's human or, animals for that matter, or machines. Things get very quickly, very complicated and so on. If you look at large language models, transformers and so on, it becomes very, very quickly. You go into many higher order variables and mixed up, and then you get into probabilistic models and so on. There is another thought that a lot of people, and I think some of the researchers, especially in universities, have, which is that maybe it is ultimately some of these models may be learning by heart almost some of the explanations. And that's why they're so good at in scientific sounding explanations. So they're actually learning by heart because they are being trained on so much data. They get the data from various places, maybe from PubMed, or in this case, of course, it's learning wrong things, but from various fake news articles and so on. Hard to figure out. I mean, all we know is right now, at least explainability is out of our realm.
Okay, would you say learning by heart? Do you mean sort of taking
memorizing? I meant memorizing.
Yeah. Okay, yeah, kind of,
because it doesn't have a heart. That's right. I mean, it's memorizing.
Okay. And Carl, who I know personally, and I know he has a sense of humor, he was replying that I think about the conversation with GPT-3 that he could see it responding that it's complicated.
Yep, to say the least.
Okay, and I think this other question was answered. Did you mean learning by heart or learning by rote? Where?
Yeah, by rote, R-O-T-E. Yeah, is this learning by heart or learning or by rote, R-O-T-E? Yeah, absolutely.
Yep.
Yeah.
All right. Let's see. I don't think there are any more questions. Anybody have any more questions they want to throw in? We're at 8:15. So, Dr. Aggarwal, did you have any more things that you wanted to have, any concluding remarks?
No, I think one of the points which is very interesting is to figure out, in my view, which will be probably a very interesting I would say, fundamental paradigm change. And somebody brought that up earlier also. Can we use things like 5 types of waves that humans, mice have to learn things? Can we use other aspects of neurological significance? I mean, we don't understand neuroscience that much anyway, but whatever we understand, can we bring those things up to actually make these systems better? To me, that's one of the biggest frontiers. I mean, yes, the debate on biases, ethics, fairness, all will continue. But in some sense, it's kind of a malleable debate because, as somebody said, how do you define ethics? How do you define biases and so on? Something which is good in one instance may be very bad in the other. But from an AI perspective, to me, that will be a very interesting area.
Okay, and Eliza says, thank you for a very interesting presentation, which one of the other Q&A participants also said, and I will echo. Can I ask one more question here? If we are going to look at other kinds of intelligence, have AI researchers looked at octopuses?
So this is an interesting one. So AI researchers, first of all, I don't think, I mean, to be honest, most AI researchers come from computer science, math, and many from physics background. Very, very, very few come from actually biology, computational informatics, and medical informatics background. So they are not looking at octopuses. They're not even looking at elegans. So elegans is a small worm, supposedly has the smallest number of neurons in it, 352 neurons. And the entire network for elegans, this small worm, was actually, neuroscientists had actually mapped out in 1986. So then that is, but we still don't understand how even elegans work. So octopuses will be much harder. What neuroscientists are actually spending a lot of time understanding are not only humans, which they realize are pretty hard to understand. I mean, we have 86 billion neurons and 1 trillion synapses, but they are trying to understand much smaller systems, mice with about 80,000 neurons or thereabouts, and elegans, which are 352. Whether any neuroscientist group has looked at octopuses, I honestly do not know.
Okay.
Leanne has a very interesting question. What topic will you be ready to present? I don't know.
So-
Let me just finish the book, ma'am, then we'll talk. But definitely next year we can, or end of this year, we can think of more topics.
Right. And then Carl, we keep having some come in. Okay. Carl asked, with all these fictional models like Skynet, Colossus, and so forth, which model could you see as a future?
I have no comments.
Okay.
I do not know what I mean.
Fair enough.
AI itself becomes so fictional at times, with some people saying that we'll have fairy tales with AI and other things. We'll have monsters with AI. I think that's probably, to me, is bad enough.
Okay. And Tom says expert judgment among humans, I believe he means, is not always explainable. Bias certainly also exists heavily in human beings.
Yeah,
okay.
Absolutely. That's right. I mean, doctors do not explain. They say, this is my expert judgment that you have such and such disease, right? I mean, comes from 25 years of experience, and it may be wrong. Absolutely.
Okay, let's see. And Eliza points out other interesting things about octopuses. And Lonnie Crispin says, your book gives the history of AI through 2049.
2050, yes. It's 1950 to, it actually starts with October 1950 to September 2049, to be very precise, because the first, in my view, that's when AI started was with the imitation game with Alan Turing. His paper on an imitation game came out in October 1950.
Okay, well, I'm sure it is a very interesting book, but thank you tonight. Several people have already expressed their thanks for an interesting presentation, and I will as well. I'm sure many of the people who didn't get a chance to express that feel the same way.
Thank you. And presumably you will, Bill and Leanne, if I can give my email out, or you folks can just give it out. Feel free if people want to ask questions, because those will be interesting for me as well. Questions or comments for that matter.
We can post it in the comment section on Meetup so that it will be perfect. Yeah, be public. Okay, thank you. And with that, we'll say good night.
Thanks, everyone. Thank you.
Okay, in recording.
Beautiful. Excellent. Thanks, Bill. Thanks, Tom. Thanks, Leanne.
Yep.